welcome a team of young interns which have come together to put up what they call Dreamer 2 with improved design and performance capable of crossing the Karman line with a scientific payload and experiment. Meet the team who have set out to fulfill the dream of Professor Kalam, the man who inspired the millions. Here is the Dreamer 2. I once again welcome the team Dreamer for their presentation. Over to you guys and all the very best.
Jitamba, thank you so much. Good evening to all of you. I welcome all of you on behalf of my team, the Dreamers. We belong to the subdomain Sounding Rocket Design, working under the domain of rocket propulsion of SSERD. My co-presenter is Pawan. So the vision of our team is reflected by the Sanskrit verse written on the top of our logo, Nabha Sparsham Deeptam, which means touch the skies with glory. We are inspired by the Bharat Ratna, Dr. APJ Abdul Kalam sir. We are actually fulfilling his dream of making a sounding rocket which he wants to design, and he wanted to see it launched. But due to some circumstances, unfortunately, he was not able to do that, and we are now fulfilling his dream. This PPT consists of all these contents. We'll first describe about the project, mission data, propulsion systems, structure design, separation mechanism, system engineering, and the last one, recovery system and launch site selection. Next. The first one is about the project. Our mission is to design a sounding rocket which is capable of crossing the Karman line, which lies about 100 kilometers above the Earth's sea level, and with a total operational payload time of 100 seconds above 100 kilometers. So what is a sounding rocket? Sounding rockets are basically two or three-stage solid propellant rockets, which are used for probing the upper atmosphere for scientific research or space research. The mission data which we collected, I'm going to present here. The first one is the first design parameter, delta V, which is the change in velocity which we'll require for achieving our target altitude of 100 kilometers. Here is the total change in velocity we estimated by considering the gravity losses and aerodynamic losses for achieving the altitude of 100 kilometers and the operational time of 100 seconds. So here is the total delta V of 3000 meter per second or 3 kilometer per second. Next. So basically here we want to grasp an idea about what should be our delta V for our mission as compared to the operational missions, different missions which are taking place in different space organizations. The next prime performance parameter which we considered here is the ISP, specific impulse, which indicates the performance of the rocket engine. The higher the ISP will be, the better the performance of rocket engine will be. Basically, it's like a mileage for the road vehicle, like car or some scooter. It's comparable or it's similar to that. So these are the different rocket engines and their respective ranges of specific impulses. So out of an intensive data survey we did for different propellants like solid propellants, hybrid propellants, liquid cryogenic, liquid storable propellants. So out of these, basically considering the design complexity and cost, and of course, by considering the high density, means we require low volume of tank. So for the simplification of our design and complexities, we selected finally the solid propellant rocket motor. So here is a schematic of the solid propellant rocket motor. The solid propellant which we selected is a new one. It's a smokeless propellant, HNIW CL20 China Lake compound. So why we selected this as our oxidizer, as our propellant? Because it gives around 14% higher energy per mass and 20% higher energy density than HMX, which is conventionally used. The propellant is basically non-polluting in nature, and it gives faint signatures of jet, like shock diamond patterns, which directly correlates with the noise of the jet. So these are the contrasting features of CL20 with respect to the different composite propellants belonging to its same family. So you can see here, it gives the ISP of 273 seconds, and these are the combustion products of it. So now the question arises, how many stages we will be requiring for completion of our mission. So by considering uh, the dry mass budget for different stages, like single stage, two stages, three stages, four stages, we conducted this estimation, and we finally estimated the fuel masses which we will be requiring. So as you can see in this graph, the two stage is giving us the most optimized number of staging for the completion of our mission. So we are going for two stages. Now I would like to invite Amin and Pawan to present their views and their data collection and their work of propulsion systems.
Hello everyone, good evening. Pawan and I will be presenting the nozzle design and the rocket engine design. So basically we wanted a very good rocket engine which would propel us to our objective. So beginning with the shape and the design, we chose a bell shaped nozzle rather than a conical or a aerospike one because it had very less weight and it gave higher performance than a conical one, and it was better for this objective than a aerospike one. And we also chose a material which would be strong enough thermally and physically to contain the heat and pressure of the rocket. So we went with a material called titanium grade 5, which is amazing at holding both two. But since it alone isn't enough at holding these two, we went at with a graphite ablation, which would ease off the pressure and temperature with the titanium. As it ablates away the graphite, it takes away with it heat and energy, which will help reduce the stress on titanium. Next, over to Pawan to explain the stage parameters.
Thank you, Amin and Nikhil. Now I go on with the nozzle parameters for both stage 1 and the stage 2. We got the thrust requirement from the system engineering team, which is around 1015 Newton, and the chamber pressure was given by the tank design team, which is around 7 megapascals. So our task was assigned to design a nozzle for both stage 1 and stage 2. Stage 1 at 0 altitude, and stage 2 at 14-kilometer altitude. So when we designed it with our expansion ratio of around 93.594 for stage 1 and 140 for the stage 2, we got the throat area which around 0.0018 meter square, and the chamber temperature was around 3591 Kelvin. Our propellant, which weighs around 27.4 gram per mole, it gave us the gas constant of 303.44. Further, on the calculating for the exit Mach number and the nozzle area parameters, we got an nozzle exit area of 0.0084 meter square. Uh, by this, our nozzle had a throat diameter of 0.107 meter, and an exit diameter of 0.1035 meter. Uh, and we could achieve this with an throat temperature of 3264 Kelvin and a throat pressure of 3.94 megapascals. Um, and the exit velocity was around 2886 meter per second for stage 1 and 2900 for stage 2. We almost designed a similar nozzles for both the stage 1 and stage 2, since our thrust requirement was same. Just due to the change in the ambient pressure at the different altitudes, there was a slight increase in the exit Mach number at stage 2, which was at 4.84 at stage 1. The exit Mach number is at 5.13 in stage 2. So these are nozzle parameters, and the total nozzle would weigh around 2.24 kgs. And over to Aditya for tank design. Thank you.
Okay, hello everyone. Good evening. So, my name is Aditya, and Varun and I are in charge of tank and structure design. Here are the parameters we obtained from the calculations. Among the materials, we consider titanium alloy, man-ranging alloy 250, aluminum alloy 15 CDV16, and among them we selected titanium because aluminum, since it has low tensile strength, it has a high mass. That was the case of 15 CDV16. It had a higher density. Among both titanium and man-ranging alloy 250, titanium was least expensive and it has more machinability. We checked about the parameters like L by D ratio, the chamber pressure, the volume of the tank, and we basically calculated using the Hooke's stress formula and basic cylinder equations. So regarding the structure, this is the outer structure. of stage 1 and stage 2. Here we are choosing aluminum alloy 2050, and here we calculated thickness using the axial stresses acting on the surfaces of the walls, and mainly we used the axial stress equations. About the nose cone, we used one Karman nozzle because of its superior performance in the supersonic higher Mach numbers, and also we chose the same aluminum alloy 2050. We had a small calculation about here, like the fineness ratio. We chose fineness ratio of 2. Next, please. And finally, the fin. Here we are planning to use trapezoidal supersonic fin. It will be a 3-fin position. We'll be using it for stage 1 and stage 2. The material used here is carbon fiber reinforced polymer. We basically considered this because of its aerodynamic properties, as well as it is used for the payload rockets. And it is fairly simple calculations. We used the fin equations to calculate the overall dimensions. Next, please. This is the final design of the rocket we were designing, and over to you, Nikhil.
Yes, thank you, Amin. So going forward with the system engineering. So based on the different designs of the components which we have for the rocket, like the payload, nose cone, fins, structure and tank, nozzle recovery system, separation system. So again, we got the dry masses for each stage to be these values. We went for an estimation with the 30 kgs for both the stages, and by the final mass estimation, we can see like we have done a great job by reducing the 2 stages dry masses, which gave us advantage with the fuel mass savings. We got around 36% savings in the fuel mass as compared if we used a single stage instead of 2 stages. So here's the altitude estimation and the operation time based on the inputs of ISPs from the nozzle team, and the mass of the propellant, which we derived by the means of mass budgeting by using delta V equals to ISP into G ln MR for both the stages. And we did these calculations by the means of Newton equations of motions because we already considered the drag losses and aerodynamic losses and gravity losses in the delta V calculation. So here the stage 1 is able to make us achieve the altitude level of 14 kilometers, and stage 2 make us reach to the 96.3 kilometers. So ultimately, by the simultaneous operation of these 2 stages, we reached the apogee of around 110.5 kilometers approximately. So the payload operational time, basically like the height above 100 kilometers it will coast, is around 10.4 kilometers, and the time at which the ultimate velocity will become 0 will be around 51.4 seconds. So the total payload operational time above 100 kilometers, which was our design altitude, is 103 seconds. So this is the flight envelope we have indicated here. This shows the different staging operations. The separation one, like the first stage will separate at 14 kilometers altitude at t equals to 80 seconds from the launch time. Then the second stage will reach the 100 kilometer altitude around 181 seconds, and then it will coast till 110.4 kilometers, which is our apogee, and it will reach there at around a time of 231 seconds since takeoff, and then the descent will take place further. Now I would like to introduce, I would like to invite Shreyas for the separation mechanism.
Yeah, thank you, Nikhil. I'm Shreyas, and I handle the stage separation mechanism design. So basically, in most of the multi-stage rockets, it's a practice to discard off the burnt-off stages in order to improve the efficiency and performance. So we carried out a requirement analysis, and we understood that we need an interstage separator that separates stage 1 from stage 2 after stage 1 burnout occurs. So there are majorly 2 things that affect staging mechanism design. One is universally applicable, that is the drag force, which helps in separation of stages post detonation of pyro bolts, which we'll be using in the staging mechanism. So we computed the difference between the drag force on stage 1 and stage 2, which is approximately around 350 Newton. In addition to that, we have a force of detonation, which is caused due to explosion of the pyro bolts. So these forces are sufficient to ensure clean and neat separation of the stages. Coming to comparative study, there are basically two types of systems: mechanical pyro systems and electromechanical systems. We carried out a comparative study, provided that the functioning of electromechanical systems depends mainly on avionics, and it's used in coupling with advanced avionics systems. But in our case, we did not need such advanced guidance systems, and in that order, we have used mechanical pyro systems. But our state separation mechanism can also incorporate avionics in it. So this is the hub type state separator that we'll be using. As you see, we are using epoxy reinforced fiberglass material for creating this stage because of ease of manufacturability and high strength that can be obtained. Provided that SSERD is a research organization, it is unlikely that there will be frequent launches or for launches for commercial purpose. Due to this reason, ease of manufacturability plays a very important role in the selection of material. So I hand over to Rohit for recovery system and launch site selection. Thank you.
Thank you, Shreyas. I'm Vamshi, and I'll be handling recovery system and launch site selection since Rohit couldn't make it today. So we were asked to design a fully recoverable rocket. Hence, we needed a recovery system that could recover both the stages along with our payload. Therefore, after reviewing several recovery techniques, we chose drogue parachute recovery system as a suitable option for our requirements. Here, the drogue parachute will gradually decrease the velocity of a rocket when it is deployed after the apogee. And after a while, when it is safe to deploy the main parachute is deployed, which will drastically reduce the velocity and which will ensure a safe recovery. Therefore, we selected the size of a parachute to be circular to increase the drag force. And the cold gas deployment device is used for the deployment of a drogue parachute. And in case of a main parachute, we used a spring mechanism to just push out the canister of the main parachute when the time is required. And coming to the mass, we estimated the mass for the recovery system in each stage to be around 3.1 kgs. Here's a breakdown of our masses in the parachute and the parachute deployment systems. It's a detailed overview of the main parachute on the left-hand side, followed by the dog parachute deployment system on the right-hand side. You can check for the components in the parachute canopy, parachute bag, suspension lines, everything we included. So it was a pretty detailed analysis, and our estimation is to be correct. And coming to the launch site, there were a few considerations we had in mind for the launch site. First is the effect of magnetic field, and second is the environmental conditions such as the speed of wind, and third, since we wanted a recovery system to be through sea, that is water recovery, we needed a launch site which was closer to a coastal area. Therefore, considering the above requirements, we selected the Tumba Equatorial Rocket Launching Station in Thiruvananthapuram, Kerala. In Tumba, the presence of equatorial electrojet, which is also close to a geomagnetic equator, made it easier for us, and it is even a coastal area helping our recovery system. Therefore, it was selected for our launch site.
Okay, thank you, Vamshi. So at last, for drawing the conclusive remarks and the future scope of the work, I would like to say the design sounding rocket D2 uses a smokeless propellant, CL20, which was proven to be efficient to make us achieve the mission altitude. The electronic systems we didn't consider here in this design, which can become the future scope of this work. The parametric design of the rocket suggests that the design is flexible and the stages are recoverable and can be reused. The rocket can carry heavier payloads also for higher altitude missions. This design reflects the uniqueness in its own regard, and it paves the way for the future developments. So I would like to introduce all of you to my team, the Dreamers, myself, Nikhil Gaur, team leader, the assistant team leader, Rohit, Aditya, and Varun. They did their work in the structure engineering and the tank design. Shreyas in the separation mechanism, Amin and Pawan in the nozzle design, and Vamshi, me and Preetham in the system engineering. So this is a collage of the computations which we did in the course of this internship by using all the online platforms. So at last, I would like to acknowledge I would like to sincerely thank our mentor, Rakesh sir, for his dedicated guidance and the coordination and cooperation by Tejas for the easy conduct of this internship and all the meetings. And at last, I would like to uh, thank my SSERD family for giving us this opportunity. So thanks a lot. It's me, Nikhil Gaur, and my whole team signing off. The Dreamers. Thank you for listening. We welcome your questions now.
Such a wonderful presentation, Team D2. Audience, you may ask your questions.
Hello everyone. Yeah, thank you. It was a very nice presentation, Dreamers. It was so good. My doubt is there the stage separation for the both stages? Means is payload getting separated from stage 2?
No, like as per the recovery system design, we got the information like we are not going to separate the nose cone from the second stage. We are going to recover it fully. The nose cone we are considering to be as an aerodynamic component in the rocket design.
Yeah. And also, can I know the functioning of detonating bolts from the separation mechanism? Means how are they gonna blast?
Yeah,
Right.
sure, sir. So basically, these bolts consist of fuses. We are using a special sort of propellant called cordite. So cordite comes in the form of filament. So this filament will be incorporated into stage one, and the high temperature in stage one ignites cordite mechanically. So what happens is these fuses run up to the pyro bolts. So pyro bolts are basically hollow bolts that contain a specific explosive that depends on the standards and various other criterion. So these pyro bolts are designed in such a way that they fracture in a specific plane. So
Yeah.
this characteristic of pyro bolts has been exploited by sounding rockets for almost many years now, including the old sounding rockets such as Nike Apache that was launched by the US and India and many other countries as such. So yes, pyro bolts are something that are highly reliable, and in case of a mishap, we have also incorporated protection within the hub for the second stage nozzle, such that even in case there are any shrapnels that might be generated due to the explosion, they don't impact the functioning of the second stage nozzle.
Great, great. Thank you so much.
Welcome.
Anyone else from the audience? All right. So thank you so much, Team Dreamer, for your amazing presentation and showcase your brilliant work. Thank you so much, guys.